Hello, we will see the designing of RMSA that we have designed in the last lecture in CST software. So just for a revision, we have selected F02 GHz, FR4 substrate, epsilon 4.3, tan delta 0.02 and H is equal to 1.6 mm. So after calculation, L turns out to be 35.64, W 42.76, and you have LG and WG. The thickness of the copper is to be taken as 0.035 mm, and the substrate of the material height of the substrate is 1.6 mm. For a SMA connector, the inner conductor diameter is 1.3 mm while the outer conductor diameter is 4.353 mm, and in between inner and outer conductor you have a Teflon material that is 2.1. Epsilon r is equal to 2.1. So we'll see the CST implementation. So I will type CS, so I will get this thing CST. New template, RF microwave, micro and RF antenna, next patch, time domain, next. Since the resonant frequency is 2 GHz, the minimum frequency I will select as 1.5 and the maximum 2.5 GHz. E field, H field and far field I have to observe. Next, finish. So before proceeding ahead, we will define all the parameters over here. So the first parameter is L. I will type over here in this parameter list. So L was 35.64 mm, W 42.76, H 1.6, then we have LG, that is length of a ground plane. So here I will type L plus 6 times H. So automatically that value will arrive over here. WG, W plus 6 times H, and the thickness of the copper 35 micrometer, or you can say 0.035 mm. So I have entered all the parameter list. Since we are repetitively using this, once only I will enter and will proceed for the design purpose. So modeling. Now we have to define the ground plane. So brick is selected and press escape. This window will appear. We'll change the name ground. Plane. X min minus LG by 2. Here it is L, and X max is LG by 2. Y min minus WG by 2, Y max WG by 2. Z min is 0 and Z max, that is thickness of the copper plane. And since copper plate, that is ground plane, and the material has to be PEC. Preview. Okay. Now above this we will have a substrate. So to take the substrate of the same size as that of the ground plane, we will pick face. We will selected the face of the ground plane and we will extrude it. and here I will type this is my substrate and the height is h, but the material is FR4 substrate. So I will select material from the material library. Here I will type FR4. Of course FR4 lossy material you have to select because it has a tan delta at 0.025. So FR4 lossy material is selected. Preview. Okay. So you have a ground plane at the back side and you have a substrate over here. Now to have a better view, just press space bar and 5. So you'll have x-axis over here, x-axis like this, y-axis like this, and z-axis coming out of the plane of this patch. Here they are mentioned, here they are shown x, y and z is coming over here. Now over here you have to mount the patch, escape. So I will type name as patch, length will be from minus L by 2 to L by 2, y mean minus W by 2 to plus W by 2, Z mean will be H plus T to, or rather Z mean should be from T plus H to T plus H plus T. Basically if you take the difference between these two, it will be T, that is the thickness of the copper, and here change the material to PC. Review. Okay, so our RMSA is done. It's not exactly RMSA, the basic structure has been implemented. Now we have to fit this antenna. So while fitting the antenna, we have an inner conductor and we'll make a through hole over here, and the inner conductor will be soldered to the top patch. So we have to remove some part of a ground plane from this location so that inner conductor should not get shorted to the ground plane. So we'll proceed for that one. So how to remove the part of the ground plane? So the procedure as follows. So that is circular in nature. Escape. Now the inner conductor of a SMA connector is the diameter of the inner conductor of SMA is 1.3 mm. So I will select the radius as 1 mm over here, so that I am removing 2 mm diameter circle from the ground plane, or that much patch from the ground plane. X center I will keep a variable x, and y center has to be 0 because we are exciting TM10 mode. So X position has to be varied for the feed, Y position will be at the center of the width. Z minimum from 0 to T. And to remove this thing, we will select a different type of material, and that material should be nickel. So I will type Ni, nickel, load, preview. They will ask the position of the X. So initially I will keep one value over here randomly, let's say 4. Okay, preview. So that hole is over here, and I will press OK. So it will ask the thing, cut away highlighted shape. Okay, so the hole has been made over here, or the part of a ground plane is removed. So now we'll connect the outer conductor over here. So we'll select the cylinder, selected the cylinder, escape. Now inner conductor. The radius is 1.3 divided by 2, because radius is diameter by 2. X position will keep X. Z mean from -5 to H plus twice T, and this has to be PEC. Review. Yes, this is the inner conductor. It is going through this hole and it is coming on the top surface. Okay, now we will have a Teflon over here as a surrounding material to the inner conductor. So in the cylinder, escape, Teflon. Now the outer radius is 4.353 by 2 and the inner radius is 1.3 by 2. X center is X, Y center 0, Z minimum -5, and it will go up to ground plane. So Z max has to be 0, but this has to be PTFE. So we'll write PTFE, or we can say Teflon material. So I have selected PTFE is the commercial name for the Teflon. So 2.1, and I will select lossy material, load, preview. Yes, correct, absolutely correct. Okay, now we have an outer conductor which is connected to the ground plane. So I have selected a cylinder, escape, outer conductor. Now the outer radius should be 4.353 by 2 plus the thickness of the copper, so plus T, and the inner radius, it is 4.353 by 2. Center X, Z minimum from -5 to 0, but this material has to be PEC. Yeah, correct. Okay, so we have modeled our SMA connector over here. It is connected to the inner conductor, is connected to the top patch, and you have this thing. Okay, so now we have to feed this antenna, so we have to excite this port. So you have to go at the back side and you have to select this face. So pick face. So as you move the cursor of the mouse over here, you will get this one getting highlighted, and I will double click on it. So this face is selected. Go to simulation, waveguide port, everything is clear, and okay. So we have excited this RMSA. Now we can simulate the antenna and we can check the result. So home and start simulation. So we'll wait. Let's have a cup of tea over here. Yes, the simulation has been completed. So we'll check the result. So on the left hand side we have 1D result plus, and we'll see the S parameter. Okay, so what is observed that after designing the antenna, we are getting the return loss not below -10 decibel. It is because of the feed position, because it is not optimized. And another thing is the resonance is taking place at 1.9. So we have to increase the resonant frequency. This is by selecting the Z parameter, Z matrix. So we have to increase the frequency. So for that purpose we have to decrease the length of the antenna, and a proper feed position has to be selected to have S11 below -10 decibel. So let us first of all decrease the decrease the length of the patch so that the frequency can be increased. So I will change this length. So just I will double click on it and I will change this length to 35.64 to let's say 35. Once you click this thing, enter, okay, and here in the home tab you can go for parametric update. And now again you start with the simulation. You have to check whether the frequency has been shifting to the 2 gigahertz or not. So this is optimization. So we'll wait for the result. Yeah, the second simulation has been completed. So what is observed, when the length was 35.64, this was the resonant frequency was near about 1.92, somewhat like that, and here it is, we are getting return loss minimum near about 2. So further length has to be decreased. So we'll reduce this L further. Let's select 34.25 and let's check the result. Okay, parametric update and start the simulation. So let's wait for the result and hope for the best. Yes, the results are obtained and yes, we are getting minimum return loss at 2 gigahertz and the value of the length is 34.25. Now we have to optimize the feed position. So that means X has to be selected in proper manner, so that 50 ohm impedance on the patch has to be a 50 ohm impedance location has to be found out on the patch. So parametric sweep, new sequence, new parameter, and I will select X and will vary X from 4 to 10 in step of 2. So I have to add 4, 6, 8, 10, 4 samples. Yes, correct. Okay, and now you start. So you are varying the feed position towards right and we'll check the impedance loci. So we'll check this thing. So wait for the result. Let's have a coffee over here. Okay, the results are calculated for X is equal to 4 and X is equal to 6. So now the parametric sweep for X is equal to 8 is running, and we can see here we have obtained a better matching compared to X is equal to 4. Now let us check the result for X is equal to 8. Yeah, the sweep has been completed and we will see the result. Yes, so this is a very good result. You are getting return loss or S11 around minus 40 decibel at 2 gigahertz. So in the result navigator number 5, which indicates that the length has to be selected as 34.25 and the feed position should be 8. Even one can further optimize this thing and one can have better return loss, but this is acceptable for the practical implementation. Just we'll see how to calculate the bandwidth. So S11 is less than minus 10 decibel, so that range of frequency is known as the bandwidth. So we'll put the cursor marker So axis marker, so 1.97, and another one is around 2.02. so that difference is the bandwidth, 2.02 gigahertz, and over here 1.97 gigahertz. So that is the bandwidth. We'll see other results. So S parameter we have seen. Now VSWR. So this is the VSWR plot. Right click, plot properties. Y-axis from 1, because minimum value of VSWR is 1 to 10, and can keep unit step size. Apply. Okay, so you can see here the antenna is perfectly, or perfect, you can say perfectly match at 2 gigahertz, because the VSWR is 1.01. the ideal value of VSWR is 1. So 50 ohm impedance at 2 gigahertz. At 2 gigahertz. So this is about 1D plots. Now we'll proceed for the 2D plots. So far field plot. So we'll see the radiation antenna pattern at 2 gigahertz. So this is the radiation pattern of the antenna. The structure over here. So this is the 3D plot, how the antenna radiates. Interesting. So I have placed the antenna structure over here. One can see it's part of it. This is the x-axis. Y-axis is perpendicular to the plane, and z-axis is over here. This is theta variation, and phi is measured with respect to x-axis. This is the 3D plot. Now we'll see the polar plot. So again in phi plane. You can see here the finite back lobes are present over here, and 3 dB angular beam width is coming around to be 93.8 degree. 98.3 degree. And in another plane it is coming around to be 100 degree. And also we'll see the surface current distribution. So for that we have to go to 2D plot, surface current, and at 2 gigahertz. So this is the surface current distribution. One has to scale it properly so that one can see the excitation of 1-0 mode. Even in this case you can see there is a 1/2 wave variation along the length, while along the width there is no half-wave variation. So 1/2 wave variation along the length means T1 for the X component and 0 for the Y component. So it is TM10 mode. You can see here the current density. Over here the current density is less because the minimum current is represented by the blue color, while the maximum current is denoted by, maximum field is denoted by this red color. So we have seen the optimization as well as the designing of the RMSA at 3 gigahertz, at 2 gigahertz on FR4 substrate. Thanks for watching. If you have any query, you mail it to me on the email ID kadam.ameya@ gmail.com. Thanks.